Hello guys, welcome back to my YouTube channel Anveshana Academy. This is Dr. Manjunath Chanapkot. Dear students, in the previous class we discussed what is combined modes of heat transfer, and also we done one numerical on combined modes of heat transfer. So come today I will solve one more numerical on combined modes of heat transfer. So first, second numerical on combined modes of heat transfer. So I will read the problem first. A surface at 250 degrees Celsius exposed to the surrounding at 110 degrees Celsius convects and radiates heat to the surroundings. The convection coefficient and radiation factors are 75 watt per meter square degree Celsius and unity respectively. Okay, so if the heat is conducted to the surface through a solid of conductivity 10 watt per meter degree Celsius, comma, what is the temperature gradient at the surface in the solid? Dear students, by reading the problem itself we can understand that there is a solid body or a plate or wall we can take. From that wall, what actually in that wall conduction heat transfer is going to take place. From that wall is exposed to the atmospheric, then what happens, some amount of heat is going to transfer through convection and some amount of heat is going to transfer through radiation. So that means what, the problem is related to combined modes of heat transfer. So now what we have to do, we have to draw one schematic diagram which is relevant to the given problem. So first what I will do, I will try to draw the schematic diagram for a particular given problem, so that you can see here, dear students. Now what actually is telling now, a surface, that means what, you can take it as a surface. Okay, so that surface I will mark it here as a Ts. Okay, that surface having temperature, that is Ts, that you can take small t or capital T, it's up to you. Notation, it's up to you. Okay, just what I will do, I will take the surface temperature, I will mark here as a Ts, that is equal to how much he has given. Yes, that is okay. Just I will first what I will do, this is what I will give the notation, then later I will list out the given data. That is okay. Okay, Ts also he has given, that is 250 degrees Celsius, and that plate is exposed to the surrounding. That surrounding is nothing but what, ambient air. Then ambient air temperature is 110 degrees Celsius. The ambient air temperature I will mark here as a T infinity, dear students. Notation, you try to make it as per your convenient. Okay, surface temperature of plate is Ts, the ambient temperature of air is T infinity, I will take it, dear students. Okay, then 250 110 degrees Celsius. Okay, fine. Then this is nothing but what, that plate is exposed, hence the convection heat transfer is going to take place. One thing, when it is exposed, right, some amount of heat energy is going to transfer through radiation heat transfer. That also he is telling, with the help of this change in temperature, both convection and radiation heat transfer is going to happen to the surrounding. That you have to consider. Fine. If it is a convection, then convection coefficient he has given, that is H. That H is equal to, you can write, that H is nothing but convection coefficient, convection heat transfer coefficient, that is 75 watt per meter square degree Celsius he has given. And when it is a radiation, right, that radiation factor also he has given, that radiation factor we will mark it as a F, that is equal to 1 he is telling, that is unity. Okay, fine. If the heat is conducted to the surface, that means what, some amount of heat is going to conduct in a metal plate. This is metal plate you can call. Okay, it is a plate actually, can call it as a plate or a surface we can take. Okay, now then when it is conducts, right, it is going to conduct, it is when it is going to transfer heat, right, that is a conduction heat transfer through a solid metal that having some thermal conductivity. That thermal conductivity we can mark here as a K. That K he has already given, that is how much, 10 watt per meter degree Celsius he has given. Then what actually is asking in this problem, dear students, he is asking to calculate temperature gradient. Temperature gradient is nothing but change in temperature per thickness of this plate. That is nothing but what he is asking to find out the dt by dx. That is nothing but temperature gradient. Okay, fine. Now dear students, one thing you have to remember here now, the area, whatever the area of the plate, right, it is a front view of what I am seeing, I can see only thickness of the plate. But when we are seeing at the top view, right, we can say area. That area means what? That area is common for both conduction, convection and radiation. That area is, through that area, what actually happening, dear students, through that area, 1 minute. through that area, conduction also is taking place, convection also taking place, the next radiation also taking place, dear students. That is radiation heat transfer. Okay, three modes of heat transfer takes place simultaneously in a plate. That type of heat transfer we can call it as a combined mode of heat transfer. Okay, now this is what schematic diagram per particular problem I have drawn, dear students. Now what I will do, I will try to list out the given data now. Now what is surface temperature of this plate? That is Ts, that I will mark here. Ts is equal to how much, dear students? That is 250 degree Celsius. Okay, and exposed to the surrounding, that surrounding is nothing but what? Air. The temperature of air I will mark here as a T infinity, that is equal to 110 degree Celsius. Dear students, you can convert this Ts in Kelvin also. How to convert? That is 250 plus 273. Then how much it will be, dear students? That also you can check here now. Okay, so now how much? So 250 plus 273 is equal to how much? 523. Yes, this is equal to Ts can express in Kelvin also, 523 Kelvin. Similarly, T infinity, that is equal to how I can do 110 degree plus degree Celsius, add 273, then what happens, dear students? It becomes 383 Kelvin. Okay, that is in terms of what? It is in degree Celsius. Sorry, it is in degree Celsius. Sorry. Degree Celsius. Sorry. Okay, it is in degree Celsius and it is in Kelvin. Okay, fine. Next, and both, as I told, dear students, initially the conduction is going to take place. Okay, that is what first we can call. It is what? Conduction heat transfer. Later, some amount of heat is going to transfer through convection. That is second, convection. Some amount of heat is going to transfer through radiation. That is 1, 2, 3. Three modes of heat transfer. They are going to take place simultaneously. Okay, the next, so the convection heat transfer coefficient. So here, first one, convection heat transfer coefficient, I will mark here as a H. That you can see here, dear students. How much he has given? That is 75 watt per meter square degree Celsius he has given. And unity, then radiation heat factor he has given as a unity. The radiation factor I will take it here as a F, that is equal to 1. Some authors they will take F, some authors they will take epsilon. Notation, it's up to you. Okay, fine. Next, unity. And if the heat is conducted to the surface through a solid conductivity, that means what? Heat is going to transfer through this metal, right? That convection radiations they are taking above the plate, but through the plate conduction heat transfer is taking place. Okay, fine. Then when the conduction heat transfer taking place in a solid body, right, it is having a thermal conductivity. That thermal conductivity he has given, that is K is equal to 10 watt per meter degree Celsius he has given, dear students. If it's so, when heat is transferring through conduction, right, that we know the equation. What is that? K minus K into dt by dx. That dt by dx is nothing but what? Temperature gradient. So he's asking to calculate temperature gradient. Temperature gradient I will mark here as a dt by dx is equal to how much. So that initially conduction heat transfer is taking place. I will write it here now. In terms of the conduction heat transfer will take place in the plate. Thereafterwards the plate is going to get heated. Once the plate is get heated, right, then what happens? That heat from that plate is going to transfer to the surrounding through convection and radiation. So that means what? The amount of heat transferred in a plate, that is conduction heat transfer, is equal to heat transfer through convection, heat transfer through radiation. The same thing I will write it in terms of equation. That means what? Q conduction. So Q conduction is equal to convection heat transfer. I will write it here, convection plus Q radiation. That means what? Initially conduction will take place in a metal, then plates will be get heated, then the heat is going to transfer from that plate to the surrounding through convection and radiation. That is nothing but what? That is equal to, that means for conduction heat transfer is equal to convection heat transfer plus radiation heat transfer. Dear students, we know the equation for conduction. What is the equation for conduction? Just a minute. What is the equation for conduction? That is minus Ka into dt by dx is equal to convection heat transfer coefficient, convection heat transfer. Now we know the equation, that is HA into, I will write it here, Ts minus T infinity plus radiation heat transfer. To calculate the radiation heat transfer, we know the equation, that is what? f into sigma into a, then ts to the power of 4 minus t infinity to the power of 4, dear students. This is the equation. With help of this equation, what I can do, I can calculate the change in I can calculate the temperature gradient, change in temperature with respect to thickness of the plate. I can calculate with help of this concept. That is this concept, what we can call, we can call it as a combined mode of heat transfer. Now let's come, we will solve this now. So what is the equation, dear students? Once again I will write the equation here now. What is that? Minus Ka into dt by dx. I will write it here. Dt by dx is equal to, what is the equation now? H into a into ts minus t infinity plus radiation heat transfer, that is f into sigma into a, the next ts to the power of 4 minus t infinity to the power of 4. Okay, so this is the equation. But dear students, you can see here now, when that area is there, right, that same area is through that same area only conduction is taking place, convection is taking place, and radiation heat transfer is taking place. Hence area is same for all modes of heat transfer. If it is same or constant, then we can neglect that area. So what I will do then I will neglect that area. So that area is remain same for all the modes of heat transfer. Then what is final equation? So final equation minus k into dt by dx. So what I can say now, a is constant here now. Okay, so that is equal to h into ts, just a minute, ts minus t infinity plus f into sigma into ts to the power of 4, ts to the power of 4 minus t infinity to the power of 4. Now what I will do, dear students, I don't know the value of dt by dx. I will keep it as it is. So therefore, what is the value of k? K he has given in the problem. How much he has given? That we can see 10 watt per meter degree Celsius he has given. That I will write it here now. So that is minus 10 into watt per meter degree Celsius he has given. Then I will write it here dt by dx. I don't know the value of dt by dx. I will keep it as it is. Then what is the value of h? H also he has given. Convection heat transfer coefficient, that is 70 watt per meter degree Celsius he has given. That I will write it here 70 or 75. Okay. Sorry, it is a 75. Okay, he has given here 75. That is equal to 75 into, what is ts infinity? That is the surface temperature that he has given 250 degrees Celsius. That you can see here now, 250 and 110 degrees Celsius he has given. So I will write it here 250 into 150. So 250 110 degrees Celsius plus f is equal to what? Radiation factor he has given, f is equal to 1. F is equal to 1 into, what is sigma? Sigma is the constant, Stefan-Boltzmann constant, that is 5.67 into 10 to the power of minus 8, dear students. Okay, into, so here because the Stefan-Boltzmann constant is in Kelvin, so for that what we will do, we have to substitute the ts and t infinity in radiation heat transfer calculations. So we need to put temperature in terms of Kelvin. So what is the Kelvin now? What is ts? Ts is equal to how much? 523 and 383. So 523 to the power of 4 minus, just a minute, okay, into what I can do? I can write it here now, 523 to the power of 4 minus how much? 383 Kelvin. 383 to the power of 4. Okay, fine. Now I will do simplification. What is minus 10? I will keep it here as it is here. Then dt by dx. Left hand side I will keep it as it is. Then I will do simplification. Okay, so now here, what is this? 75. Yes, 75 into what I can write now? 250 minus 110 into the next, that is okay, plus what I can do, 5.67, that is one you can neglect, 5.67 into 10 to the power of minus 8. Okay, minus 8 into what we can write, 523 to the 4 of 4. The next minus 383 to the 4 of 4. What is the answer? You are going to get 13,522.2. So now what I can do now? Now I can do here dt by dx is equal to I will take this 10 this side. So then 13,522.2 divided by, here it is a minus 10, then minus 10. So therefore what I can do now? So therefore dt by dx is equal to minus, then it becomes what? 13,5 to find 2, then it is what? dt is degree Celsius, because degree Celsius, then dx will be in terms of meter. Hence the final answer is minus 1352 degree Celsius per meter is the temperature gradient, dear students. Why it is minus sign? Minus sign indicates what? The temperature is going to decrease. This is explained by what? Fourier's law. Okay, that means what? Decrease in the temperature we can mark here as a negative. Okay, this is the final answer. Dear students, I hope you understood today's problem. Thank you. Please do subscribe and like and comment, and your support helps me a lot. Thank you.